Hello, everybody. This is part 3 of our series on motion, energy, and gravity, and this time we're going to tackle Newton's law of gravitation. So Newton's law of gravitation says that two bodies attract each other with a force that is directly proportional to the mass of each body and inversely proportional to the square of the distance between them. Here you can see that written as an equation. Let me show you that as a figure. So here I've got two masses. They have mass m1 and mass m2, and they're a distance apart d, and they're pulling towards each other according to gravity. And the force that they are pulling each other with is given by this equation. G is a constant. It is a universal constant. It just stays the same all the time. M1 is the mass of one body, M2 is the mass of the other body, and D is the distance between them. So depending on what the masses are and how far apart they are, that will determine what the force of gravity is. In this formula here, the big M would be M1, the little m would be M2, and R is just the same as D as the distance between them. So here we have the sun, and here we have, in this case, the Earth, but a planet going around the sun. And it is this force of gravity that is giving us that pull, okay? That's what we need to exist in order for us to stay in orbit around the sun. So let's go back to thinking about that ball on a string. Here I've got someone there twirling the ball around their head. There's a tension on the string, and we can see that as it's going around, it's going to keep going around. But if the string snaps, then the ball will go in the direction A here. It won't go off in the direction C. It won't keep going in orbit. It will just keep going in a straight line with whatever velocity it had when the string snapped. How strong that force is depends on a number of different things. You need to have a stronger pull if you have a shorter string, but you also need a stronger pull if you have a bigger mass on the end. But you know this instinctively. If you try to twirl something around your head, if it's something that is on a very short string, you're going to have to spin it really fast. But you can let it out and spin it more slowly. But if it's more massive, then you'll have to spin it faster again. Now, we know that it depends on how fast it's being spun. The force that's needed depends on how fast it's being spun, what the mass of the ball is, and how long the string is. And it can be written as an equation like this. This is actually called the centripetal force. And so I've got the mass of the ball, the speed of the ball, and the distance from the center of its motion. Okay. And we can apply this to the Earth too. So here's the sun and here's the Earth. And as it's going around, there must be a force just like this that depends on the mass of the Earth, the speed of the Earth, and its distance from the sun. Okay, so we just said that the force that is causing us to stay in orbit is gravity, and it's given by the universal law of gravitation. At the same time, that it's given by this formula for the centripetal force. So now we can equate these two and say my force that's giving me circular motion is just gravity, and I can start to rearrange the equations. So here I've just made them equal to each other. I'm going to do a little bit of canceling things. So remember, r squared is just r times r. So if I cancel the r here, I can cancel just the squared there. There's an m and an m here. In this case, the big M would be the sun, and the little m would be the Earth. Here, the little m is the Earth, so we can cancel those m's too. And so now we have something that is just gm over r equals v squared. Okay. Now, if we're assuming circular orbit, then the speed is just given by the distance that the planet travels in a given time. The length of a full orbit, circular orbit, is just the circumference, which is 2 pi r, and the time it takes to go around is p, the period of the orbit. And so we can now put this into our equation up here. So gm over r equals 2 pi r over p all squared, and then I've put that out like this. And now all I've done is I've moved the p squared up and the gm down, and then this r, by multiplying through by r, on both sides, I get rid of the r here and I get an extra r here. So we get an equation that looks like this. Now this may look somewhat familiar. Kepler's third law says that p squared equals a cubed as long as you're using the right units. But it can be written as p squared equals some sort of constant So it's p squared equals k a cubed, and that will work for any units. Now, if we look at this, and remember that a is the semi-major axis, but that's the same as radius if you're talking about a circular orbit. And so we can see here that this is exactly the same as Kepler's third law. But now what we've got is this constant here that is related to the mass of the sun. So pi is just a constant, g is just a constant, 4 is obviously a constant. So as long as we know how long it takes a planet to go around and how far away from the sun it is, we can calculate the mass of the sun. That's the only thing we don't know. Let's dig into that just a little bit deeper. So actually, you can do this a little more carefully and show that what you get is that p squared equals something times a cubed, but where that something is both the masses. So this would be the mass of the sun and the earth, or the sun and Jupiter, or earth and the moon. I'm not going to prove that here. There is another video on my YouTube channel that does that. But for planets, the mass of the planet is negligible compared to the mass of the sun. This M with a little circle with a dot in, the circle with the dot is the sun symbol for the sun. And so this is the mass of the sun. So I can basically say, okay, M1 plus M2 is basically the same as just M1. It's a little bit like me weighing myself when I get up in the morning and then putting on one sock and weighing myself again. The difference in my mass is so little that it's really not going to register on the weighing scale. And so it's a little bit like that with the planet. The mass of the Earth compared to the mass of the sun is so small that you can just basically write it off. And so now you come back to what we had before, and we've got p squared equals this constant times a cubed. And so we can check this. We can work out what's the time it takes for Jupiter to go around, how far away is it? What's the time for Saturn to go around, how far away is it? And we can use that to make sure that it works. But this works for other things too. So in this case, I'm looking at a planet and the moon. So I've got a planet and a moon going around each other. Now, all I've done here is to rearrange this, because what I want to do is to arrange it so that I get the mass of the planet out. So I've moved the masses part up here and the period part down here. And so now I've got an equation that looks like this. Just like with the Earth and the sun, the moon and the Earth, the moon's mass is pretty much negligible compared to the Earth. So you can basically ignore it. So now, as long as you know how long it takes for the moon to go around the Earth and how far away it is, you can work out the mass of the Earth. You can also do this for any other planet and its moons. And so what we have is we have an equation that is the mass of a planet is given by a moon's semi-major axis of orbit and its period. So if we can find something that's orbiting a star, a planet, an asteroid, we can work out how much mass is contained in there. And that's because of Newton's law of gravity.